Good afternoon, everyone, and welcome to the webinar on the role of grid-forming IBRs in shaping RE integrated power system. I am Ruchi Kushwaha from Grid Integration Lab. We would be starting the event shortly. Before starting the event, I would like to mention a few things. So this entire event is being recorded at our end. Due to paucity of time, we have an open Q&A session of 15 minutes only. Therefore, during the course of event, if the audience has any question, I request you to kindly use the Slido link and the QR code that will be shared in the chat box. We will be taking up the questions directly from it there. Also, the post-event material will be uploaded on our Grid Integration Lab website and LinkedIn page. So first, let me walk you through the agenda item for this event. Let me share my screen. Yes, so the event will start with welcoming of all the speakers, participants, and the introduction of the speaker. Then we have an interesting presentation by Professor Zakir Rather from IIT Bombay on grid forming converter technology um, and its role in IBR-dominated power systems, followed by another insightful presentation by Mr. Jean-Philippe Hasler on grid forming functional specification for STATCOMs. After this, we will have a Q&A session where we will be answering the questions asked by the participants, and then the event will end with the vote of thanks. So first and foremost, I would like to introduce our speaker, Mr. Jean-Philippe Hasler. Mr. Hasler has received his MSc degree in electrical engineering from the École Polytechnique Fédérale de Lausanne, Switzerland in 1986. He joined ABB in 1986, where he was developing control system and protection algorithm for multi-terminal HVDC. Then, since 1993, he is conducting power system and control studies for different FACT applications and currently holds the title of Senior Principal Engineer at Hitachi Energy, Sweden. Welcome, Mr. Jean-Philippe Hasler, to this webinar.
Yes, thank you very much for the introduction.
Hello. So now let's move ahead with the web event. I would like to invite Professor Zakir Rather from Grid Integration Lab, IIT Bombay, for his presentation on grid forming converter technologies and its role in IBR-dominated power systems. Zakir sir, over to you.
Thanks, Ruchi. A very good afternoon. Or good morning, depending on where the participants are from. So the first presentation, as Ruchi mentioned, it will be on grid forming converter technology and its role in IBR-dominated power systems. This presentation will primarily focus on grid forming technology introduction, basics, and then we will move into a bit of what are the capabilities of these grid forming technology based IBRs, and then how these IBRs can help grid in various support services that it can potentially provide to the grid. And then eventually we will look at some of the grid code regulation aspects in the context of grid forming converter technology. Before going into the presentation, I think Ruchi already mentioned it. Again, for those who might be joining now or have joined just a while ago, there will be question answer session that we will take up at the end, and the questions will be taken through this tool known as Slido. You can directly, you don't need to log in, you can directly scan this QR code, or the link is already in the team's chat box. You can actually access that, and you can post your question query over there. There is also a provision of voting which question you think is more popular. You can vote on the question or query from other participants. So So those who will have any queries, please feel free to put those queries in this Slido tool. Now, the introduction part, I generally start my presentation around renewables with this by flashing this slide. I strongly believe we do have a global climate emergency, and India is not immune to this climate change that is happening across the world. We are also experiencing several impacts or issues with this climate change. And little bit introduction for those who are not very well versed with the Indian grid. We have in India, this is global actually, global in capacity, installed capacity of wind, which has been getting added to the system since 1980s, early 1980s, compared to solar, which started a little late. In line with global trend in India also, we have started integrating wind somewhere in 1980s. We have as of now around 48 gigawatt roughly installed capacity in India, and we are adding more and more wind as we move forward with the RE targets in India. Similarly, solar again is actually pacing up very fast, which most of the participants would be already familiar with. And in line with that, again in India, we are integrating solar PV generation at quite a bit fast pace. We have right now roughly around 93 gigawatt of installed capacity. This is 2023 December figure, but as of now we have around 93 gigawatt of solar PV installed capacity, and in India we have target of integrating higher share of renewables with around 450 gigawatt from solar and wind predominantly, and 500 gigawatt of non-fossil fuel based sources. So in similar to other grids in the world, some of them have already transformed significantly in terms of RE integration. In India, we are in a stage where a lot of renewables are getting added, and a lot of renewables will continue to get added to the system. This is just again some numbers. We have as of October 2024, 156 gigawatt of renewables installed capacity installed capacity in India, out of 454 gigawatt total installed capacity, which accounts for around 35% of the installed capacity of renewables in India. And these are some of the states that we have relatively higher share of renewables in India, because India has some of the states which are relatively more rich in RE compared to other states. So these are some of those states which are relatively higher. Now, coming to the impact of the renewable energy integration, there have been, predominantly all the renewables that we have around the world, exceptions are there, few demonstrations, and some of the handful of the plants are there from the grid forming technology, but vast majority of this is grid following technology, these IBRs that we have in the system across the world. And they have been introducing several challenges in the grid, particularly technical challenges, and some of them can be broadly attributed to intermittency and variability of the renewables, solar and wind, non-synchronous nature, which is impacting the frequency stability, transient stability, and other stability issues in the grid, power quality related issues. So the grid has been, experiencing these different challenges, technical challenges, with the increased penetration of these IBRs. So hence, the need for looking at how to address those technical challenges in the grid with high penetration of renewables, and in the process, these are some of the examples, some of the impacts that we have with the IBR integration. You can see the inertia is one of those parameters of the grid, important parameters of the grid, that actually declines for very obvious reason with the increase in IBRs, because we are displacing the rotating mass in the grid. So as a result, there are frequency stability concerns that come around, particularly with the maximum handling of maximum rock off in the system following any generation load, sudden generation load imbalance in the system. So this is a simple test study that we have done here at IIT Bombay to show, how for the same system and same contingency with the increased penetration of renewables, the frequency nadir and the runoff is actually deteriorating further and further by increased share of renewables in the system. Similarly, grid strength is also getting impacted, as you can see here. Some of one of the case studies on ESO grid here, short circuit level you can see is broadly. Of course, it depends on the generation mix and all that in a given control area or given area of the focus. But in general, with the increase in renewables and displacement of the rotating mass in these conventional generators, as a result, because of that, the short circuit capability of the system is getting broadly deteriorated, and that is other side of the impact of this. So there's just a couple of impacts that, for the sake of showing that there are technical impacts that IBRs actually are introducing the system, and that actually makes it challenging for the grid operators to handle the grid operation under high penetration of renewables. Now, little bit introduction about the grid forming technology. So we, as I mentioned earlier, we have been having this grid following technology across the world, through which we have been introducing these renewables into the system. And this grid following technology started primarily with what we call as grid feeding technology, where the converter, to be precise here, inverter, is injecting a controlled current from this IBR into the system that you can see. So it has a control over the current, but it does need the voltage and frequency. It does need the external grid to be established there before it can be actually synchronized with the grid, and then power can be injected with the grid. So this is what we call as grid following technology. It has grid feeding, which is primarily controlling the active power injection, while predominantly maintaining unity power factor, so hardly any reactive power exchange with the grid. And most of the small scale renewable plants in the grids across the world and in India also are actually of grid feeding technology. For example, rooftop PV and other smaller capacity generations, RE generations, are of grid feeding technology. Well, as grid supporting technology of the grid following includes additional grid support services, which includes reactive power support, which includes frequency support, and in some cases inertial support, and other ride-through capabilities and those grid support functionalities. So this is in simple terms the grid following technology, IP converter technology, that is predominantly in the IBR technology in the utility scale or otherwise plants in RE plants in the system. Now the grid forming converter technology is primarily here what we are trying essentially is to mimic the conventional generator, because if their RE source is RE technology is able to behave similar to conventional generator, nothing better than that, because the grid operator knows very well how the conventional generator, conventional technology, these power plants are being operated, how they help the grid, because technically speaking, these synchronous machines are beautiful grid elements in the grid, from the grid operation perspective, from the stability, and because they have those inherent capabilities of grid support services. So therefore, this is somewhat kind of in that direction in grid forming technology, where the behavior of the conventional generator is being attempted to mimic it with this technology. So this operates as a voltage source technology rather than the current source here, where you can see similar to exciter control in the synchronous generator, which controls the voltage. Here also the voltage, internal voltage, is actually being controlled, and then the load angle in the corresponding to load angle control in the conventional synchronous generator, which we control through primarily governor control. Here also the voltage angle is actually controlled with internal angle here also. So you have internal voltage, EMF, equivalent of EMF, and then the angle is actually being controlled in this So it behaves similar, not obviously identical, but similar to the conventional generator in its response characteristics. So that's what is essentially grid forming technology. There are several definitions of grid forming technology, but for the sake of simplicity, I have put this definition here. Basically, the inverter technology which is able to control the frequency and voltage, which can establish the grid on its own, with the local control at the inverter level, and is able to maintain constant or at least near constant voltage phasor at its local value for short time scale, primarily subtransient and transient time scale, is can be classified as grid forming technology. Now, what are the major differences in terms of functionalities or capabilities between grid following and grid forming technology? So the grid form, as I said, grid for GFL technology is actually able to control the current magnitude at its terminal. It does need PLL for synchronization, and it does need PLL throughout its operation. So it's not that we synchronize the inverter with the grid and then that's done the way we do in the conventional generator. No, here you need continuously PLL there, which will keep the inverter synchronized with the grid. So that, and then there are several issues with the PLL, particularly during transients and all that, that introduce additional challenges with grid following technology. Technically speaking, you cannot achieve very high penetration of IBRs in this with this grid following technology, because there are a lot of other challenges that are introduced in the system. There are stability related issues, as I briefly mentioned earlier. It's not stable for the black start capability, to be precise, at the start. Later on, once partly the black start has the grid has recovered or started, then they can supplement that, but on their own they cannot be participate in the black start capability of the system. It does have the faster response, but there is a delay associated with it in terms of the measurement of the parameters and the control loop delays that are there associated with this. As I mentioned, it needs the external grid. So in contrast, the grid forming technology, it can regulate voltage magnitude and frequency from the inverter side. It does not need the PLL because it is, as I mentioned earlier, it is behaving similar to conventional generators. So the moment it is synchronized, it remains synchronized with the grid. 100% IBR system is, technically speaking, possible with grid forming technology. Particularly in weak grids, grid following technology has challenges, a lot of challenges, and the grid forming actually does have that capability to operate in weak grids, and then it improves the system strength of the grid as well. It does offer black start capability. It has inherent inertial response, which is not precisely the inherent inertial response as that of a synchronous generator or synchronous machine, but it is very close to that, or we can say it is relatively way faster than grid following technology. So it does have that inertial support advantage in terms of its fast response. Enhanced power quality, it can actually improve the power quality, which is another major concern with the IBR technology. Damping of oscillation is, we have seen around the world also some of the oscillation driven grid events. It does help in the grid oscillation, damping the oscillation as it can operate in stand-alone operation. So these are some of the broader comparisons between the capabilities of grid following and grid forming. Now, if we look at closely, the difference is predominantly in the control, the way we control the converter. The hardware broadly remains same, not identical. There are changes in terms of the current capability of the converters and other storage requirement and all that, but it's predominantly around the control strategies, control philosophies that we apply to this converter technology to make it grid forming. So in terms of the control philosophy or control schemes or control technology, we can divide broadly it into Drude-based grid forming control, virtual synchronous machine control, virtual oscillator control, matching control, and there are subcategories, several subcategories, which in the interest of time will not go into those. But you can say broadly, these are some of the major categories in terms of the control of this grid forming technology. For example, this is group-based grid forming technology here at IIT Bombay. We have done this, kind of test to see the response of this grid forming, technology. So this is a small 9-bus system here, test system, and we have synchronous machine, grid forming inverter 1, grid forming inverter 2. Each of the generator is, of capacity of 100 megawatt, and then there is a load change of here 75 megawatt, and you can see the response here. This is the response of the conventional generator, and this is the response of grid forming IBR, this power plant 1 and 2. So you can see this fast, and it is actually providing faster response, and relatively magnitude as well is also relatively better, and this is the impact on the frequency. So what we can see here, it is the nadir of the frequency nadir is improved in term because of this grid forming technology. However, if you look at the conventional generator, its nadir is actually going relatively down. But the rock-off, if you can see here, rock-off is better, improved in the case of conventional generator, because there's an inherent inertia that it provides, well as it's not as good in the grid forming case because it does not provide same response in terms of the inertial control. Similarly, virtual synchronous machine, the difference here is, here it is it's providing this PF group control based on the frequency change, it accordingly changes the power. So here, kind of the swing equation that we have in the dynamics of the conventional synchronous machine is being tried to introduce here in the overall control. So that's why it's the name virtual synchronous machine. And similar cases here, you can see the response here. And here, basically, again, similar output, but the rock-off here is relatively better in grid forming case compared to the previous group-based, control topology. So there are others also. Again, these are the sample cases that we try to show in terms of these capabilities, responses of these different converter control topologies for the grid forming inverter. Now, looking at the capabilities of these IBRs, which use the grid forming technology. Now, if you look at what are the capabilities that at unit level they can provide, when I say unit level, it is inverter level for solar PV, WTG level for wind turbine generator. So they do have this better ride through and fast fault current injection. They can provide that inherent inertia that I was mentioning earlier. They can provide damping capabilities of the oscillation. They can actually be used to improve the quality compared to grid following technology. That is at the unit level. Now, if you look at the system level, of course, the services that are being provided at the system level, they stem from the unit level also. So it's all linked. So at system level, they can provide the frequency and voltage support services. Not that grid following technology does not provide. They do have the capability and they do provide even as of today as well. But the frequency and voltage support capability of this grid forming technology is relatively better than grid following technology. System strength enhancement, as I mentioned earlier, at the system level, it can provide the black start services as well. If you look at the plant level, so this is one of the case studies, rather a field demonstration example, where there is a wind power plant here, 69 megawatt, which are operating in grid forming mode for 6 weeks, May, June 2019. And the control topology of the grid forming, as I mentioned, there are several such control topologies that was used in this particular wind power plant is virtual synchronous machine, VSM mode. And there were naturally occurring events in the grid to which it responded. So, for example, there has been this interconnection outage, which led to around 1 gigawatt loss of in-feed, and eventually the maximum rock-off of 0.11 hertz in a sliding rock-off, and the frequency deviation of 0.5 hertz at the system level. That can be seen here. And now this is the response of this wind power plant here. the blue one is actually the total response, some of the turbine output power, and this is some of the converter reference. So this one is basically the reference that was power reference, and this is actual power output. So which actually indicates, or you can see here, this is the additional power it is injecting in response to the this frequency deviation, and the rock off is shown here. So which indicates that it is able to provide the inertial response to the grid following this large frequency deviation and rock off in the system. Similarly, there is one more field example of this battery energy storage system with grid forming technology interfacing, which is again VSM mode of the control, 30 MVA 8 megawatt hour battery, this is the response of this battery storage plant, where this BSS in this South Australian grid on 16th November there was this trip of Haywood interconnector. If those who are following that these kind of events in 2016, also this Haywood interconnector was partially involved in that grid outage as well. So this is actually resulting into basically the over frequency on this side of the grid, and as a result, you can see this battery energy storage system interfaced through the grid forming technology. It is actually changing its power in order to. It was 6 megawatt. Now it is decreasing this power in response to the increase in frequency. So what is actually shown on these right side plots is that the frequency change starts somewhere here. This is the zoomed version of the frequency change here. But if you see the current that starts decreasing from this IBR interfaced BSS is actually earlier than the frequency change. So which indicates that this providing the inertial response even before the change of the frequency of the grid. Similarly, we looked at another aspect at IIT Bombay in terms of the system level studies. So here, what we have done is we considered that we have a system which is technically 100% IBR based system. So this is the modified 39 bus system test system, where we have 10 generators, grid forming technology, total 6,220 megawatt generation. It is roughly 6 gigawatt peak load. And we have a constant readiness of 1,000 watt per meter square considered for this. And we simulated this 650 megawatt generation outage in this system. So that is this PV power plant 6, which is connected to bus 36. Now, the response you can see here of these other grid forming power plants, here we have shown only for PV7 and PV8 as a representative results of this study. So you can see here, power plant 7, PV power plant 7 is closer to the disturbance, while as power plant 8 is a little bit farther from the disturbance. So you can see here the response of these two, the DC link voltage of the plant, which is closer to the disturbance, that is PV7, is actually getting more disturbed. Or you can see here it is providing more response here, the current response from the DC link compared to the power plant 8, which is farther from the disturbance. So indicating that lower the electrical distance of this power plant with respect to the disturbance location, it is providing actually relatively more response here. That is also reflected in terms of the voltage here and the power output. So you can see here in the output of the power plant, this is power plant 7. This is the total power output of the converter on the grid side, whereas this one is the power output of the blue one is actually actual power output, DC power output of the PV modules of this plant, which indicates that we are able to inject additional power here at the onset of the disturbance to provide inertial response to the grid. And the voltage, DC link voltage of the plant is actually decreasing. This is upper limit, this is lower limit, because the plant was operating on high voltage side of the MPP before the event. and therefore once the event was there, the voltage was reduced to actually provide this support. So we have done this power hardware in loop study as well in this to test the same capabilities of this system, where you can see on the PV side the change because of the event, that outage of the plant. There is a change in increase in the power output here, and there's a decrease in the power voltage as a result of that certain increase in the loss of the generation. And this is the DC link voltage. Again, DC link voltage is reducing. The frequency, as the frequency is reducing, here also DC link voltage is reducing, indicating in the power hardware how this is responding the grid forming technology to the events. Similarly, this is another study we carried out here. Now in this case, this is more at a system level frequency control in terms of the reserves and other frequency support. This is again the same system, 100% IBR based penetration, and then we have here a mix of solar PV and wind power plants in the system, and the readiness is variable, load is variable to actually look at the more realistic scenarios. So what the aim was here is actually the reserves, entire reserves. Of course, here there is no conventional generators, so the entire reserves are actually frequency reserves are provided by these solar power plants of the system, which are of the grid forming technology. So this is the readiness variation that is considered for this window, and this is the wind speed variation, which is again considered for the wind power plants. And this is the load demand that we have in the system, which is varying. So you can see, the solar power plant output is actually changing. I'll talk more about it in the next slide. And this is the wind power plant output in the system. So what we did is we considered that 7% of the load should be the reserve. To dimension, simple dimension of the reserve, we considered 7% of the load equivalent has to be the reserve from the solar power plants. And then what we proposed is adaptive frequency regulation and the reserve maintenance in the system. So this is, you can see here, this is the reserve requirement, and this is what is actual reserve maintained in the system from these power plants. The first one is actually, you can see here, the power plant 3, which is keeping the reserve. So this is, we have considered the symmetric reserve requirement, 7% upper side, 7% down reserve. And then you can see here, until this 1000 seconds, this plant is actually maintaining the up reserve and the down reserve in the system. What is happening around this time, since the power plant output is decreasing, on the upper side, up reserve side, it is maintaining that 7% of the reserve, 7% load equivalent reserve. But on the downside, post this, there is now decrease in the reserve because of falling output of the power plant 3. So then automatically what is happening is, post this point where we are now falling short of the reserve on the lower side, the power plant 1 is actually starting contributing to it. So power plant 1 starts decreasing its power output to maintain this down reserve as well, equal to the up reserve in the system. And this is the frequency of the system in this case. And then again here we did this hardware in loop study. So where you can see this is the change in irradiance, and this is the reserve maintained in the system, the blue one, and this is the upper limit of the reserve. This is lower limit of the reserve. So if you see the once this these values are changing, so accordingly it is adapting to maintain this constant reserve in the system. Similarly, the voltage is changing to respond to that, and this is the frequency of the system, where all these grid forming inverter-based sources were used. We also looked at here at IIT Bombay on the impact on the grid strength. So this is a simple case study how the grid forming technology can actually improve the grid strength. So in this case, we have this power plant with grid following PV power plant with grid following technology of 200 megawatt, and then it's detailed modeling. Though here in the single line diagram it is showing aggregate modeling. So aggregate representation. So we have in one case the battery storage system interfaced with grid following. One scenario is PV plant with grid following interfacing battery. Another scenario is PV plant, but with grid forming interfacing of the battery storage. So in scenario one, where we have the grid following interfacing, we have this effective short circuit ratio at 33 kV bus of 5 here. But in scenario two, where we have the grid forming technology interfacing this battery energy storage system, in that case, this battery is not active. This system is not active. So for a fair comparison, so with this grid forming technology, the short circuit ratio at 33 kV bus has improved from 5 to 6.21. Now the other aspect of this is black start capability of these grid forming technology. It has these additional capabilities in terms of capability of handling inrush currents in the transformer, line charging current, which is very much required for the black start plant. So again, we did one power hardware in loop study here in the lab, where we try to look at this 9-bus system with 2 grid forming inverters. One grid forming inverter is connected to bus 3, another is connected, grid forming 2 connected to bus 1. And there is a conventional generator connected to bus 2. And these are the capacities of these systems. So here is the sequence of the black start we actually conducted in this study, which is starting from here with this grid forming 1 inverter, which is connected here. It starts with this, and then at every different intervals of time, we are charging the line, switching on the respective circuit breakers. And then you can see here grid forming 2 is being connected here at this, which is power hardware in loop. And then it is accordingly, again, the circuit breakers are switched in sequentially in order to energize the whole system. So as a result with this sequence of these switching, we were able to actually have a black start of this small test system in the lab. This is the field example of the black start capability of this wind power plant, where it is demonstrating that this black start of voltage black start of this system and of these feeders. So there are feeders that are connected at different points in time, and you can see this inrush current is, which is possibly the charging current of the line and maybe transformer inrush current as well that are reflected in the spikes here, and as a result it is actually black starting some of the distribution feeders at 33 kV level. So these are some of the capabilities of this grid forming technology, but not everything is by default good with grid forming technology. So there are challenges and limitations with grid forming technology. Although there are stability issues of this grid forming technology in strong grid, if carefully not addressed or taken into account, it can actually lead to some of the stability issues in the strong grid. So we have a reverse issue here. We had an issue in the weak grid with grid following, but we have challenges in the strong grid with the grid forming technology. Energy buffer is, of course, required here if you need to provide inertial response, and for sure if you need to provide the black start capabilities. So that is an additional, hardware requirement, infrastructure requirement. Higher current capability is required because there are inrush currents that immediately flow into the system. There are methods to control the current output of the grid forming technology, but yet because of this voltage source technology, that similarity with the conventional generator, there is this initial current that can overshoot the rating of the converter, or you can say the converter rating, switch current rating need to be higher than what otherwise it may be required in the grid following control topology. And coordination of grid forming control with the source behind it, particularly if it is a mechanical system in wind turbine generator, all those complexities are there. Now coming to the last leg of my presentation, this is about the grid code regulations, which is very important component of the grid operation, particularly with the renewables. that we have had, we are already having across the world, whichever country is having the renewables. Almost all countries have grid code regulations for IBR-based technology. Now, what is, they're different in terms of the grid forming technology when it comes to grid code regulation. So ASO has already the grid code regulations in that, these are some of the requirements for the grid forming technology, that it should provide symmetrical ability for exchange of the power with respect to active rock-off response of the power. Phase jump is another additional aspect with the grid forming technology, which is not there as such in the grid forming technology. So phase jump is another requirement that is required here, because it is something which needs to be critically considered and factored when there is a grid forming technology. Damping power requirement, because as I mentioned earlier, there is a capability of the damping of the oscillators in the system. So therefore, if the grid forming technology, there can be a grid code requirement for demonstrating the capability of damping of active damping power requirement. Similarly, other requirements are there that are relatively additional, you would say, in the grid forming technology. This is again, in this case, the real power output in this case, you can see 100% change in per hertz, 100% change in power per hertz, which is quite a bit faster here. You can see the requirement in terms of these grid forming technologies. Now, when we say grid code regulation, there is always the testing aspects of the compliance aspects of the grid code regulation. So these are some of the additional requirements that in terms of the capabilities, and then later tests that you need. Reactive power capability is already there in the grid following. Also voltage control, active power control, and other write-through capabilities. But you can see the damping control is the additional one. Active rock-off response of the power, active phase jump of the power requirement, active damping power that I mentioned is another capability. These are some of the additional capabilities that need to be demonstrated. For example, this is in the extreme events, 50 to 52 hertz at the rate of 2 hertz per second withstand capability, 50 to 50 hertz at the rate of 1 hertz per second withstand capability, 50 hertz to 47 hertz at the rate of 2 hertz capability. And this is the full range requirement. For example, here you can say 50 to 50 hertz at the rate of 1 hertz per second over a 2-second period, and then it will stabilize for 5 seconds. So there are these additional capabilities that could be asked, could be the requirement from the grid code regulations for these capabilities of these grid forming technology. This slide is showing some of the tests that are done here. For example, for the grid code regulation that I showed in the previous slide for grid forming. So this is 2 hertz per second, you can say, withstand capability here in this case. And this is the power output here. It is actually responding according to the power output. Here is some current limitation that is coming into picture. And this is the rock-off requirement. Again, you can see 2 hertz per second test for this grid forming technology. There are many of the Arduinos would be probably familiar with. There are efforts already in place at NCO level for these grid forming technology, and the tests and the functionalities and the capability requirement for this grid forming technology that is shaping up at different regional and national levels. This is again some of the voluntary specification for grid forming inverters in 𝐒𝐫𝐢𝐝. So there are additional voluntary requirements. But broadly, what I wanted to put out here is that there is in grid code regulation, there are specific requirements of the grid forming inverter technology that has to be part of the overall grid code compliance when it comes to grid forming technology, in order to exploit the capabilities of this emerging technology in this IBR space. So that is all from my side in this presentation for now. Again, I would like to remind that there is this Slido here, QR code for those who join later. There is a Q&A session we will take up at the later part. And you may ask the questions over this platform, that is Slido. So that's all from my presentation. So without taking further time, I would request Jean-Philippe to please proceed with your presentation. Over to you, John.
Yes, thank you, Professor Zakir. I will try to share my presentation. So I will present our understanding about the grid forming functional specification for STATCOM. And I think that is, I think probably this grid forming definition you have for IBR, that mean device which is put in the net to provide energy. It's a bit different probably for a STATCOM. A STATCOM, if you remember what is a STATCOM is a device say located somewhere in the transmission system and supposed to stabilize the voltage. That was the initial functionality of the STATCOM. And now, of course, it has been extended somehow to not only say provide voltage support, but also to support the frequency. First, I would just like to see, I think maybe a bit repeat about what Professor Zakir have said, but the importance of the grid service we have to provide and what is the new requirement that the STATCOM has to provide to the grid. First, if we remember in what you see in the left side of the slide, it is a bit the conventional grid. The conventional grid, you have a transmission system, and connected to it, you have very large synchronous generator or plant. And all this synchronism or coordination about the synchronous speed was done with a machine. And with very robust machine having a very large inertia, that means the grid was very stable. Even if we are connecting some small wind farm turbine or photovoltaic, which was not very common a few years ago, not having, say, a solid link to the frequency or to the synchronous speed, it was said the grid was dominating or conducted by the large generator. Nowadays, with the introduction of or replacement of many of these huge generator synchronous machine, it has been replaced by wind turbine, for example, photovoltaic, or sometimes by HVDC, and all of them, I think, have result in the reduced inertia, because all of this new device does not really respond to any frequency change in your system. We have also an issue about voltage stability, because voltage stability means we are often, especially for the wind farms, having a wind turbine located very far away from the onshore connection grid through very long cable, which mean a wind farm, for example, located at a very remote place, cannot directly control the voltage of your system. Synchronization is also an issue for this wind turbine, especially when they are connected to an offshore platform, for example, or remote location, because normally they are connected to very long cable. And all this wind turbine, it's known that they can be stable at the conditions that they have a sufficient short circuit power at their connecting bus. But with this long cable, that is not ensured anymore. And grid strength, that is a bit the same thing. I mean, we have more and more extending our grid to remote place, which means that the grid strength, of course, is reduced just by the fact that we are connecting different devices in a very remote location. And that, of course, everything, this new change, it's end up that we get a new requirement from the TSO and for related to the renewable integration. But I will also to mention that the TSO requirement normally are very often valid for all this device or IBR, but not sometimes not directly connected to a STATCOM. Now, just to mention a bit more, what was say in the past, what was the challenge for the STATCOM, and the only challenge was to improve the voltage profile. I would say voltage profile. It means the mean value of the voltage. But it was not a challenge to say to compensate for the small variation. That was in the past the purpose of a STATCOM. And normally doesn't mean to maintain the voltage. It was necessary to use the STATCOM, but we have also used SVC technology, which is a TCR and a filter. So the only condition was to have, say, a variable means to vary the megavar. And that have been called, I think, in the past as a megavar service. But now we have seen from the, involving a grid, that means integration of a lot of renewable. And we see that many associations, that means starting from what we have been mentioned now from the TSO, Migrate, Academy Page, and FinGrid or many TSO, they say what we have to do for a STATCOM is first to do what we are doing in the past is to maintain the voltage profile. That means to get a stable voltage. Is we have to we have to contribute to the grid strength, which means that if any type of converter start to inject some fluctuating power or reactive power, that should not result in a big deviation in the voltage or in the frequency. We are also talking about the support for weak grid, and that is especially to support some remote device or generation, which are maybe at very remote place. And then you have also to be ensured that all these converters are able to operate. That means they can inject their power, and that is what we call about support weak grid, which is exactly the same functionality. I have to say we have to increase the string strength. A frequency support, that is typically when you lose, and what Professor Zakir have shown before, is when you lose a large load in your system or you trip some subsystem. So we have a frequency nadir, a frequency change, and the functionality of our STATCOM or enhanced STATCOM is to stabilize the frequency. That means to limit the frequency nadir, especially to limit the frequency and to restore the frequency as faster. What in principle, what this type of what we call frequency support is often related to some TSO, what they say it's an inertia service. That means you provide inertia to the system. And then what maybe the most important is to compensate for harmonic, or it's a harmonic compensation, but mainly is to say avoid or to damp impedance resonance you may get in the system. Because when you have a long cable having some capacitance or many filter or capacitor bank, all of these devices create some resonance in the system. And it's very common nowadays to get resonance at second harmonic, between second harmonic and third and fourth, fifth harmonic. And one role of the STATCOM is not really to damp the harmonic level, but is more to damp the impedance resonance. Just to show what is the service, to resume a bit the service, what we have to provide now with the STATCOM, and maybe I start from the top one. It's a fault current. A fault current, that is what happened during a fault condition. And in the past, the fault current was provided by generator. But normally, wind farms, especially the one we have nowadays, are of course provided some fault current, but not always, or at a reduced. And one task for the STATCOM now is to improve the fault current. And that's the main purpose. It's to ensure that the protection system, which is based on the fault, on the current, short circuit current, will work as it was before. Then we have to increase the strict strength, of course. And what is the main task is also to improve the voltage control of the grid, because we have to improve the voltage control not only for the steady state, but also for transient behavior. And that is what also says a fast dynamic voltage control. That means if we have an oscillation caused by subsynchronous resonance, it's very important that we provide the proper damping. A system restart, of course, is very important. When you restart the system, that means our STATCOM should, in principle, behave like a generator. A frequency control, we have mentioned that, is mainly to what frequency control is mean when we have, for example, a line switching, or you are connecting a heavy load. That is to specially control the frequency when we have a large phase step in the grid. That means if you have a large phase step in the grid, and it's very important to damp the oscillation which will be result from the step. And then, of course, we have also the inertia support, as I've been discussing before. Now, what we see, just to compare a little, what is the difference with grid forming, the way we want to say implement for our STATCOM and a generator. And we can say, finally, the difference between the two are really similar, because a generator, you can say you have a kind of voltage source, which is controlled by the swing equation, mainly the phase angle, and you have an impedance. And the impedance is, say, it can be say it's equivalent to the subsynchronous impedance. And using this approach, so first is to say that we are not controlling directly the current through this device. That means is what to say, that is a bit the difference between a grid following, a grid forming control. That means the current will be the direct relation between the voltage you have at the primary and minus, say, the voltage you have emulated here, or it's a generator, and it will be finally defined by the virtual impedance or by the impedance. That means we are not controlling voltage. The only things we have to do is to control this voltage to finally limit the power you will have through this converter in case of rock-off or extremely high phase jump. But basically, our control will behave exactly as a generator, which means also when we have, say, resonance in your grid, that means you provide a parallel, say, impedance to your grid, which will be defined by this virtual impedance or impedance to damp the resonance. Is what I'm showing here. That means if you have, say, distortion in your voltage through this impedance you define, which will have to be defined, you will automatically, say, maintain the voltage to an ideal or to a sine wave. So what we have implemented in our STATCOM is finally extremely simple. What we say, we want to emulate a voltage source, what we call internal voltage, and we want to define an impedance. And this impedance is maybe here what is the different definition of this impedance. I think in some grid forming control implementation, it is meant that the impedance is equal to the physical impedance of the converter. But in our case, we want to implement a virtual impedance, what's called virtual. That means it will be, say, an impedance which is defined by a control system. And this impedance has to be represented as a simple resistance plus inductor. And I will just maybe define why we are using a resistance and not only, say, using the physical impedance, is to give damping, sufficient damping for any kind of, say, disturbance in your grid. Because we, exactly like we have said before, if you would have used a pure inductance, it's extremely difficult to, say, to define a current which is stable when you have a very strong grid. So it's why for us it's extremely, as a STATCOM connected to a grid transmission system, even if it's strong or weak or whatever, it has to be included with a damping which is defined by this resistance. And if we do that, I mean, it's does not mean, of course, is no guarantee, but normally having this resistance and this virtual impedance, that you will at least stabilize most of the disturbance you can get in a grid. Just also to maybe to mention about how we have, say, control our STATCOM in the past, which what we call it grid forming, grid following control. And as I think the Professor Zakir have mentioned, that we are using a PLL as a reference angle. But the main task of the STATCOM in the past was to generate a current according to some law, for example, voltage variation. And the main task was to generate a sinusoidal current, especially reactive current, and normally try to minimize the active current or the active power. And that the task of minimizing the active power was only due to, because we have to maintain the DC capacitor in our STATCOM to be constant. But it was absolutely no other law, or we are not taking into account if you have, say, a disturbance in the grid to modify the current. We are trying to be completely decoupled from the grid disturbance. The difference with the grid forming nowadays is what I have said, the current through the converter will only be defined mainly by the virtual impedance. That means each time you get a perturbation in the grid, and that means the current will be defined by the virtual impedance. That's it. The only times when we have to change the voltage to the phase angle of the voltage, and that has to be, say, done very slowly or with what we call a bandwidth below a certain frequency, is to, for example, to control the power or the energy we want to exchange between the STATCOM and the grid. Is the same way when we have a voltage control, we want to change the magnitude of this voltage, not fast, for sure, using the voltage control. And you can see in this scheme, we are now controlling power and reactive power, P and Q. We are not controlling any current, which was, say, expressed in the past in the 𝐑𝐄 system, having a reference of the PLL. And now we don't have any PLL at all. The only part we have a keep from the GFL is the current limiter. And that the current limiter is will be only activated for extremely short time. That means exactly when we have a transient is to limit the valve current, to protect the valve current, but after the valve current has been, say, limited to a certain value, we are going back to the power or energy control to adapt the power reference such that the current in the STATCOM is again below the valve current, and we still keeping all the time the behavior of this virtual impedance. One task has been to illustrate a little bit what do STATCOM or enhance STATCOM. I mean, we have a typical load grid representation here when we have, for example, some wind farms with long transmission line. You may have a machine. You may have load, which has very often power electronic load nowadays. That means are controlled by some converter or whatever. And we have also some converter, GFL, STATCOM, for example, traditional SVC or whatever. And our task mainly is to first to maintain, for example, the bus voltage at a certain point. We have to damp harmonics or impedance you can, which is resulting for the long cable and capacitance you have in the grid. And also very important, we have to minimize the interaction you will have between different devices, because we know nowadays that we have a lot of interaction, for example, between wind farms and maybe STATCOM. And that is what we call differential mode. We have also to damp, say, the complete power mode or oscillation you have between the complete plant and the big grid. And to do this task, what we find out is to have our STATCOM to behave like a RL circuit with a relatively robust voltage source. And doing that, we are just saying that the impedance of a STATCOM will be in parallel to the what we call a ideal grid equivalent. That means a strong grid, or maybe not grid, but very robust, which has exactly the same characteristic. That is the main purpose of our STATCOM. A basic control. For the basic control of a STATCOM, I think we have to differentiate the control behavior in different zones. And we define a zone what is regarding the positive sequence, how it should react when we have a disturbance in the positive sequence, but also a negative sequence, how it reacts, especially when how the STATCOM will react when we have a fault in the grid, which can be one-phase, two-phase fault disturbance. And if I start by the positive sequence, you see that for frequency, I mean, the frequency is defined as a frequency of power you can observe. It's not the frequency of the AC signal, which is above 5 Hertz. That means we know that the converter for the positive have to behave exactly as a constant impedance only. It should not be any control, say, who can change the behavior for this frequency. At low frequency, we want to be more, have a stiff control. That means we want to control the power or the inertia, depending on the rock-off, for example, and we want also to control the reactive power. And that finally defines the steady state operation. And in between these two types of control, between constant impedance and say a stiff control, you will have some kind of gray zone, what we call how the damping is done between these two different modes. For example, when you provide inertia, we know that when a machine provides inertia, it have, say, the power increase, and then we have an overshoot, and then we have a poorly damped oscillation. And is what we are talking in this scheme is how we define the damping when we have a rock-off, for example, or how we define the damping when we have a step in the voltage you control. For the negative sequence is very more simple. For the negative sequence, we always keep the same impedance, whatever is the frequency. That means it does not, we don't have any special control. The negative sequence current will be only defined by this virtual impedance, nothing else. It's only in case when we have to limit this negative sequence, then we will have a, say, a current limiter, or we will change, say, the operating point of the negative sequence control. But nothing will happen in the very high frequency or relatively high. What I mean is above 1 Hertz or something like that. So just to resume, what is the equivalent circuit of our normally is STATCOM? When here we have the virtual impedance, what is called sometimes is virtual impedance, we have different definition, but it's called control impedance plus physical impedance of the converter. And we have the transformer, and all these are constant. This definition of control impedance, I think, is taken from the German TSO, how they have defined the control impedance. And this control impedance has to include resistive part. That is for the positive sequence. And we have, for the positive sequence also, we have of course to define this internal voltage, which will be mainly driven by relatively slow power control or inertia control. For the negative sequence, we have get exactly the same impedance. And for the negative sequence, our internal voltage is normally set to 0. That means the current is only defined by the negative sequence perturbation and divided, say, by the total impedance you have. No other control should interact this current. Also, I would like to define also what is quantity we are observing when we are talking about gridforming. And in fact, it is power and reactive power. Power means only the power due to the positive sequence of the current, the same as for the reactive power. And this power and reactive is more or less equivalent to what we call the active power current, which is a current component causing the power at nominal voltage. It's the same for the reactive power. When it's negative sequence, we define a negative power or power of the negative sequence, which is simply the product of the voltage, negative sequence voltage times the complex conjugate of the current. And this is a current given in the power or real and imaginary part, which has a current which is in phase with the bus voltage. We are comparing the result. And that is a bit different from the reference system we are using in the PAL, using a PLL. We are referring a current based on a PLL or a bus voltage, which was just created artificially somewhere. Just to show a very simple example how the STATCOM should react, for example, when we have a voltage step or voltage decrease in the bus voltage, the yellow curve here is a voltage step from 1 per unit to 0.9, and that shows a current or the voltage, sorry, in alpha beta, and is how the voltage behaves. That means what you see is only a change in the magnitude suddenly. And you see what is the direct, contribution from the STATCOM. And the current generator is only defined by the XV and RV, or the virtual impedance. And what you see here, we have a instantaneous almost response to the current, almost no delay. The only thing you see, it's a kind of DC component. You see that the current includes a DC component, which is damping out very rapidly, and that is depending on this virtual resistance. Normally, we want to have the damping of this DC component to be done in 1 or 2 cycles. Now, if we look at this current and translate it to or quantify in terms of power and reactive power, so you see that we have a step in active power now, or I will start by the reactive power, and the reactive power change, the power in per unit is proportional to the XV. And you see also a step in active power, and the active power in this case is depending of RV. And you see that the oscillation you see in the power, which is have a frequency of about 50 Hertz, is not really an oscillation, but that is a oscillation you will observe when you have a DC component. So this overshoot is only to say that we have a DC component in the power or reactive power. So I will not talk about the step in the phase angle, but a very different same response. That means is no delay. And just to mention how we define the response through differential equation, and you get a second order of the equation. I will probably go out of this diagram explaining what is the requirement about the virtual impedance behavior for different frequency, for positive sequence and negative sequence. Here I have a definition of our power control, which is finally a power control with emulate a swing equation, a simple single equation. The only difference here is we can control the damping of the equation. That is the main difference you have between a machine and our 𝐸-STATCOM, is the damping can be controlled, and normally we use higher dampings that we will use for a machine. A definition of the situation, you have the plant voltage control that we are using a similar plant control. And this was trying to show the difference, how we define the response of the 𝐸-STATCOM depending on which perturbation we have and the frequency, but I will probably step out that one. Try to explain, maybe that is if I spend 1 second, here we are comparing, say, the impedance or the behavior of a 𝐸-STATCOM against a machine. And you see that the blue curve has a response of 𝐸-STATCOM, and the red one is a response of a pure STATCOM. That means a STATCOM without energy storage. And the difference is the breaking frequency. That means is when we have our power control start to be activated. When we have a 𝐸-STATCOM, we start to activate the power control when the frequency is below 1 Hertz. For 𝐸-STATCOM, we are a bit higher. We are maybe at 20 Hertz. And here you see in yellow, that is a response of a machine. And you see the machine includes some resonance. And the first resonance you get is when you have your swing equation, which are not very poorly damped. That means you get this kind of resonance, which means will define the damping of the swing you can get after a transient. And we can see that with the 𝐸-STATCOM, it's required that we have a much higher damping. Also, the damping of the DC. We see that in the 𝐸-STATCOM or STATCOM mode, we try to damp very fast the DC. That means we don't have any resonance. But in the case of a machine, you will get a resonance at 50 Hertz or closely, and that gives this sometimes very poor damping oscillation during some transient. Proof of concept, I will just do very fast if I'm allowed. This is just to compare two results. When we have, say, a three-phase fault for a wind farm's application, and the purpose of the 𝐸-STATCOM first is to, after voltage recovery, is to damp the overvoltage. That is the most important. And after a while is to damp the subsynchronous resonance you can get between a wind farm, for example, and the grid. And that is probably the same example. Okay, I'm sorry to be too long. Thank you.
Thanks, John, for the interesting presentation. Thank you. So even though we are running a bit late, I think we will try to take up a few of the questions. There are several queries, but some of the queries we will try to take up. Based on the ranking that is they're taken care by this Slido. The first question that I can see at the top is there a need of integrating IBRs with grid forming control in Indian grid scenario right now? So let me try to answer this question. As I mentioned, this grid forming technology is emerging technology in IBRs. And therefore, as the technology advances, it is likely to get introduced in any system as we move forward. Now, in terms of the Indian scenario, to be precise, in my opinion, there is a need for streamlining the existing IBR technology that we have already in the system. As I mentioned, we have primarily the grid following technology in Indian grid and across the world, primarily. So one is that we need to further strengthen that technology in terms of the support capabilities, compliance with the regulations and the requirements. Grid forming, as I mentioned, it is emerging and coming into the system. And once it comes, if it is there in the grid, be it Indian grid or any other grid, as I mentioned, there are several new support capabilities that this technology is offering for the grid stability. It would certainly improve the grid performance, technically speaking. But of course, there are several other factors. So broadly, yes, if there is grid forming technology, even now, it is certainly going to help the system in many ways. But at the same time, as I mentioned it, even before that, the existing technology can be further streamlined and strengthened in terms of its grid support capabilities, compliance with the requirements existing regulations. So hope that answers the first question. Second, again in the order of ranking, is how did equivalent short circuit ratio is CR improved with PV plus grid forming and compared to PV with grid following. So in this ESCR calculation, there is a coupling of these parallel inverters that comes into factor, which basically looks at the sensitivity, voltage sensitivity takes into account. Since the grid forming converters, as I mentioned, have characteristics similar to, not equivalent, similar to conventional generator, their control over the voltage and that sensitivity factor that is there in the overall calculation of that ESCR is actually relatively better than grid following because of the control capabilities and the fast response, and that improves the short circuit ratio. Not a conventional short circuit ratio, which is simply short circuit MVA divided by megawatt capacity of the IBR that's to be connected there. But here, as I mentioned, it includes the sensitivities of these parallel IBRs in terms of the voltage changes, which takes into account the electrical distance between those points. So that's how if it is equivalent short circuit ratio is actually improving with grid forming technology. Next question is, in Indian context, are there many grid following resources in distribution grids? Do we anticipate grid forming technology in distribution grids? So as of now, the vast majority of the distributed generation technology in terms of primarily rooftop PVs that are there is, as I mentioned, it is vast majority of that is grid following. Primarily under grid following also, as I mentioned, there are two categories: grid feeding and the grid supporting. It is grid feeding primarily, which tries to maintain the unity power factor. There are some grid forming technologies where in the distribution system where it is used as for standalone systems, because for standalone system it is a PV inverter based. For example, you have a remote area. We have several areas in India which are not, let us say, do not have, some of these remote locations do not have the access to the main grid. There are PV systems already in place, and then for that you need to actually have a grid forming technology. So at that level, there are grid forming technologies already in distribution system in those pockets, but predominantly in the distribution system in India, we have grid following technology with primarily grid feeding mode. That is the next question. And then the next question is, what is the hardware and software changes in grid forming and grid following converter or IBRs? I think Jean-Philippe will be the right person to answer this question. Over to you, John.
The difference, it's I think we have to differentiate between IBR and STATCOM again, I think. I think we have a different definition in the grid forming in the STATCOM. When we introduce this virtual damping or resistance, and that probably make a big difference. Right. But in terms of implementation, what it's probably more simple to do it, because what is the difference is we get rid of the PLL. So it's no question about to know if the PLL is stable or not. And we are just introducing this virtual impedance. And I would say that is a major change we have for us STATCOM, of course.
Right. Great. So in addition to that, in let us say inverter-based grid-forming IBRs, there are additional requirements in terms of, as I mentioned earlier, also hardware in terms of the storage requirement and the design aspects, the current rating, and few more hardware aspects are there which are different relatively in the compared to grid following technology. The next question is what challenges do you anticipate in the role of grid forming technology in scaling the RE deployment in to reach 500 gigawatt non-fossil fuel target in India? So as I mentioned, we do not have as such the grid forming technology right now in Indian grid, particularly at the utility scale power plant level. But with the advancement of the technology, it is likely to get introduced into the Indian grid as well. And while transitioning towards this 500 gigawatt, I do not anticipate the percentage share of grid forming technology is going to be significantly high, because this 500 gigawatt is by 2030. So therefore, whatever proportion that may come in Indian grid by that time, in my opinion, is going to primarily broadly at the system level strengthen it further. Nevertheless, some of the challenges that I mentioned towards the one of the slides in the presentation, those factors need to be considered while considering the grid forming technology in Indian grid. Next question is, does a virtual impedance contribute to subtransient reactance during short circuit faults? John, would you like to take this question? Does from STATCOM perspective, does virtual impedance contribute to subtransient reactance during short circuit faults?
Yeah, I mean, so in the STATCOM, we don't have any subtransient, transient, or what. We just have one reactance, and is always constant. Is only when we have a current limiter or we have to change, then we can say we very short time modify this impedance. Before and after we change again our voltage source. That means once the current has been limited for transients, then we return back to the impedance which has been predefined. So it's not subtransient, it's only one impedance, constant all the time.
Yeah. So in IBRs, it does have a role in transient this reactance, depending on how fast the control is. It certainly can get introduced into the system. So in IBR grid forming technology side, in my opinion. Next is, does any standard IEEE IC exist to test if the inverter is grid following or grid forming? If yes, major players, industries, are they following any sort of these tests for their converters before their delivery? John, again, I think you would be the right person to reply this question about if there is any practice of testing. Of course, the functionalities I already mentioned, you also mentioned, if there is any practice of testing in the industry, for this grid forming technology.
Yeah, I think we refer most of the time, one of official standard is, I think, the VDE standard, which is a standard and proposing some test procedure, how to test it. And I think we see also from IEEE, which is under development, I think the standard, which is name P2800, if I remember, series, but still in an early stage. Otherwise, we have some standard, but issued by TSO, which are not official standard. But the only standard I know is, I think, is from the VDE standards.
Fine. So I will take the last question because we are already, overshooting by already 15 minutes by now. This question is, what are some relevant studies standards applicable for integration of IBR in Indian context for an interconnection process? Well, there are several studies and standards that have been conducted around this RE integration in India. There are, in addition to studies, there are grid connection regulations, technical connectivity standards. There are CRC Indian Grid Code Regulation 2023 is the latest one, which talks about the regulations around RE particularly, and then the connectivity standard that is also there in terms of standard regulations. And then there are individual standards there, IEEE standards, IEC standards. Some of those standards are also adopted in the Indian RE sector. And there are other several studies on the grid integration of renewables. It will be difficult to point out all those different studies that have been done, but there are several. Some of them we have been also doing. So in case you are interested, whoever is pointing this question, please feel free to visit our Grid Integration Lab website. There are several reports and publications around RE integration that we have also carried out. So with this, I think in the interest of time, I will stop here. Unfortunately, we could not take all the questions because there were many of those questions. I don't think we were able to take even half of them. Hopefully, these questions were more relevant as per the ranking that showed up in the slide. So with this, I would like to hand over to Ruchi for the concluding vote of thanks. Over to you, Ruchi.
Thank you, Mr. John and Professor Zakir for this incredible session. So with this, we have come to the end of this event. I would like to go ahead with the vote of thanks. First and foremost, I would like to thank our speakers, Mr. Jean-Philippe Hasler and Professor Zakir Rather, for taking out time from their busy schedule for this event. I would also like to thank the GL team for their engagement and coordination during the event. Lastly, I would like to thank all the participants for joining us in this webinar and making this an event remarkable. Thank you all and have a great evening.